This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss some technology solutions and problem extensions for the 2021 AP Calculus exam, free response question AB2. My name is Steve Kokoska. I'm a professor emeritus at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing the free response question, and then the scoring guidelines used at the AP Calculus reading. And I'll focus on the solutions given in these guidelines and the specific presentation required to earn each point. I'll present the solution to each problem in a little greater detail than given in the scoring guidelines. I'll show you how to use technology to explore and answer parts of this question and to confirm solutions where appropriate. And because the free response questions are usually very comprehensive, I'll suggest some problem extensions. These are additional AP Calculus type questions, some that are associated with the information given in the problem, and some may be calculator active. Just a reminder, this is a calculator active problem, and that means that students may be required to use the calculator in some or all parts of this question. In this problem, the velocity of a particle p and the velocity of a particle q over the time interval 0 to pi are given, and we know the position of each particle at time t equals 0. In part A, we need to find the position of both particle p and particle q at time t equal 1. In part B, we need to determine if the particles are moving toward each other or away from each other, also at time t equal 1. Oh, and of course, we need to explain our reasoning. In part C, we're asked to find the acceleration of particle q at time t equal 1 and to determine if the speed of the particle at that time is increasing or decreasing. And finally, in part D, we need to find the total distance traveled by particle p over the time interval 0 to pi. Now first, you should notice that the format of the AP Calculus scoring guidelines has changed as of the 2021 exam. Here are two important observations. There are no longer any 2-point parts. Every one of the 9 points in a free response question is parsed out. And the scoring notes used by the readers are presented in the scoring guidelines. Part A was worth 3 points. Now, to solve this problem, we need to use the net change theorem, or really the fundamental theorem of calculus. The first point was for explicitly presenting one correct definite integral on the way to solving this complete problem. So either this definite integral or this one must be presented. Now the first point must be earned in order to be eligible for the second and third points. The second point is earned for adding the initial condition to at least one of the definite integrals and finding the correct position. So the second point is awarded for this calculation or for this one. And remember, the final numerical answer must be correct to 3 digits to the right of the decimal, rounded or truncated. And the third point is for finding the other position. If the student omits the differential in an integrand, that is the dt, then they may not earn a position point if the presentation leads to an ambiguous integrand. And, in general, unlabeled answers are read left to right or top to bottom. Part B was worth 2 points. The first point was for determining the direction of motion of one of the particles. This point cannot be earned without reference to the sign of v sub p of 1 or v sub q of 1. However, it is not necessary to report the explicit value of v sub p of 1 or v sub q of 1. But if a value is presented, it must be correct as far as reported up to 3 places after the decimal. The second point is earned for an explanation based on the signs of v sub p of 1 and v sub q of 1, and the relative positions of p and q at time t equal 1. Recall that these positions were found in Part A. Part C was worth 2 points. The first point was for finding the acceleration of particle q at time t equal 1. However, to earn this point, the student must explicitly connect this acceleration to v sub q prime. So that means that the first point cannot be earned for a bald or unsupported value of 1.027 or 1.026. The student cannot simply write a of 1 equals 1.027. There must be some indication that v prime equals a. The second point is earned for reporting that the speed is decreasing with a sufficient reason. Now, the response does not need to present a value for v sub q of 1. The sign is sufficient. To earn the second point, a response must compare the signs of a sub q and v sub q at t equal 1. It's not sufficient for the student to consider only one sign. After the first point is earned, a response like velocity and acceleration are of opposite signs at t equal 1, so the particle is slowing down, earns the second point. And the second point may be earned without the first, as long as the correct value for v sub q of 1 is presented. Part D was also worth 2 points. The first point was earned for presenting the correct definite integral, this expression. That is, the mathematical expression used to find the correct answer, the total distance traveled by the particle. This point can be earned by presenting a sum or difference of definite integrals. In other words, some students found the value of t at which the velocity changes sign. They used the definition of the absolute value function, and they split the definite integral into 2 parts. And the second point in Part D is earned only for the correct answer. So in this case, a bald or unsupported value of 1.931 earns no points in Part D. Let's take a closer look at the solutions. And remember, this was a calculator active question. So let's consider the use of technology to visualize and solve some of these problems. Once again, to solve Part A, we need to use the net change theorem, or the fundamental theorem of calculus. In each case, the final position of the particle is equal to the initial position plus the net change in position. Here's how I solved this problem using technology, specifically the TI-Nspire CAS calculator. First, I defined the velocity functions v sub p and v sub q. And then, looking ahead, I defined the position function for particle p and for particle q. And finally, I evaluated each position function at time t equal 1. Now, remember, the student needs to report these numerical answers correct to 3 places to the right of the decimal, rounded or truncated. In Part B, we need to consider the sign of the velocity of each particle at time t equal 1 in order to determine the direction of movement of each particle. So, using technology, I found the actual values for v sub p of 1 and v sub q of 1. And this tells me that particle p is moving to the right and particle q is moving to the left at time t equal 1. Now I know the direction of movement of each particle, but before I can answer the question, I need to know the position of each particle at time t equal 1. But we found these values in part A. And at time t equal 1, I know the position of particle P is to the left of particle Q. So finally, because particle P is moving to the right and particle Q is moving to the left, the particles are moving toward each other at time t equal 1. To answer part C, we need to consider the signs of the acceleration and velocity of particle Q at time t equal 1. We already found the velocity of particle Q at time t equal 1 in part B. The value is -1. And we know the acceleration is the derivative of the velocity. So, using technology, I found a sub q at 1. Because the acceleration and velocity have different signs, the speed of the particle is decreasing at time t equal 1. In part D, the total distance traveled by particle P over the interval 0 to pi is given by this definite integral. And just a reminder, the student must present the mathematical setup that leads to the correct answer in order to receive full credit. Here, I simply evaluated the definite integral on a calculator screen. The total distance traveled is 1.931 units. We weren't given any units in this problem. And here's a way to visualize this result. This is a graph of the function y equal the absolute value of v sub p of t. The definite integral represents the area under this curve from t equals 0 to t equal pi. And I found the same answer on the graph screen, 1.931. Let's use the information given in this question and consider a few additional problems. First, find the net distance traveled by the particle Q over the time interval 0 to pi. Contrast this question with part D. Here, the integrand does not include the absolute value function. I used technology to find the net distance traveled is minus 0.215. Now this means that particle Q ended up 0.215 units to the left of where it started at time t equals 0. And here's a visualization of this result. The net distance traveled by the particle is the net area bounded by the graph of the velocity function and the horizontal axis. These two areas look almost equal, and in fact, there's just a little more area in the region below the axis than above, and therefore, the result is minus 0.215. And here's a part F. I like this one. Find the first time t at which the particles are at the same position at the same time. Now the first thing I did to explore this question was to graph both position functions. The blue curve here is the position of particle P as a function of time, and the green curve is the position function for particle Q. Now, this graph suggests that the particles P and Q are never at the same position. But the graph isn't enough. I've got to confirm this analytically. To understand the position function for P a little bit better, I considered first the velocity function. Now, I know that the velocity function oscillates between -1 and +1. And knowing a little bit about the sine function, the most that we could add or subtract to the initial position of particle P is 2. So the farthest to the right, or the largest possible value for x sub p of t, is 5, the initial position, plus 2, or 7. The position function for particle Q looks like it has an absolute minimum value near pi over 2. So the first thing I'll do is look for the critical values, and there is only one at t equal 1.8. Now, let's see if we can pull all this information together. For t in this interval, v sub q of t is less than 0. And for t greater than 1.8, v sub q of t is greater than 0. This means that the position function for q has an absolute minimum value at t equal 1.8. And using technology, that position is approximately 8.139, which is greater than 7. The farthest particle p could be to the right. Therefore, the particles are never at the same position at the same time. Cool problem. And I encourage you to try to solve this problem in a couple of other ways. And here's one more typical calculator-active AP Calculus type question. A particle is moving along a horizontal line with velocity function given, and we know the initial position of the particle. First, find the position of the particle at time t equal 5. And then determine the number of times the particle changes direction on the interval 0 to 2 pi. In part C, find all the times in the given interval at which the speed of the particle is 0.2. And part D asks another question about speed. Is the speed increasing or decreasing at time t equal 5? And finally, in part E, find the displacement of the particle and the total distance traveled by the particle over the interval 0 to 2 pi. I hope this video gives you a better idea of how to solve this free response problem, some good ideas for additional practice AP Calculus exam type questions, how to use technology to solve some of the parts of this problem, and to explore, confirm, and visualize results. I think this problem presents some good opportunities to discuss and visualize particle motion. And just a reminder, there are lots of valuable resources on the TI website. There's material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.